Hi, my name is Blanca Belzunegui, and I'm a student of second Optativo in Somalapeta. During this video, I'm going to present my physics work to you. This optional work consisted of inventing or choosing a problem, choosing some variables, and making a study of them. The problem I've chosen is about a magnetic induction lamp. This is its formulation. A magnetic induction lamp is connected to a ballast of 150 watts of power. As we can see in the picture, inside this lamp's bulb we can find a cylindrical conductor whose radius is 0.02 meters, which is this gray thing here, and a copper bobbin made up of 200 coils, which is this orange thing here. Through a process in which the magnetic field converts part of the mercury into gas, the electrons with the gas energy crush into the mercury atoms. This way they earn energy and consequently jump to a superior level, even if they get back to their original position very quickly. During this last process, they lose energy, which is emitted in the form of ultraviolet photons. This ultraviolet light is immediately absorbed by the atoms of the phosphor coating, which in a similar process ascend up level and descend to the original one in next to no time. But some of the energy is lost on the way again, and therefore this ultraviolet light gets out of the bulb as visible light, as the energy of the emitted photons is smaller. This visible light is measured in lumens. You are asked to calculate the lumens produced by the lamp with the aforementioned characteristics. The variables we are going to be working with are the power, the number of coils, and the radius of the conductor. In order to solve our problem, we need to make some intermediate calculations first, such as the resistance, the intensity, the length of the copper wire, the magnetic field, the ultraviolet photons per second, and the visible light photons per second. This way we'll reach our final result, which in our case is the lumens provided. So here we've got the Excel, which shows the value of our intermediate calculations and the result of our original problem. This value, in any event, is approximate because I had to round off all the numbers to 2 decimal places. Here we can see the calculations and the constants. And here we've got the study of the first variable, which is the power. It varies from 25 to 250 watts. And this is its graph. Here we can see that when the power supply to the lamp increases, so it does the quantity of lumens that this lamp emits. This means that the quantity of lumens is directly proportional to the power supplied. This can be easily represented in our GeoGebra. This is our GeoGebra. Here we can see a brief summary of our exercise. And, well, here's the bulb, which is connected to a ballast in which we can change the power. So here in the bottom center part of our screen, we can see the result, which in our case is the lumens provided. And this will let us play with our variables, this problem. And so see how the emission of the lumens change depending on them. So first and foremost, I would like to point out that there's a reason for which this lamp's light's color is yellowish orange once we switch it on. And it has to do with the color temperature. I've done some research and found out that the color temperature of this type of lamps tends to be between 2700 to 4000. If we look in the Kelvin scale over here, we'll realize that this means that the light should be of this color, which it is. So, we were with the power, and as we have said, as we increase the power supply to the bulb, the emission of the lumens should be stronger, and that's exactly what happens here. I should say that these lines here, each of these lines represents 25 coils. So, our second variable is the number of coils, and we can see it here, which varies from 25 to 250 and 52. So, we can deduce from the declining form of the graph that the quantity of lumens is inversely proportional to the number of coils. At first glance, it might look a little bit odd, but if we pay attention to our calculations, we'll soon realize that it makes sense. So, when the number of coils decreases, so it does the value of the resistance, which means that intensity will rise. Consequently, the magnetic field will also be stronger, and in the end, the amount of lumens provided will also be bigger. So we can also represent this in our GeoGebra here with the number of coils. So we have deduced from our Excel is clearly represented here. We can easily see how the emission of the lumens shrink as the number of coils increases. In any event, the emission we obtain with 25 coils is much stronger than the one with 250. Sorry. So, last but not least, we've got the radius of the conductor, which is here. And our problem varies from 0.01 meters to 0.1 meters. So, in its graph, we can see that the smaller the radius of the conductor is, the higher the amount of lumens we are provided, which means that the quantity of lumens is also inversely proportional to the radius of the conductor, as happened with the number of coils. This can also be represented in our GeoGebra. So whenever we make the radius of the conductor bigger, we can see how the emission of the light is weaker. And on the other hand, we can see how it gets stronger when the radius is smaller. So as a general conclusion, we can affirm that if what we're looking for is to increase the number of lumens, making the smallest change possible, the most reasonable thing to do would be to decrease the number of coils and the radius of the conductor, and besides increase the power supply to the lamp. And on the other hand, if our aim is to achieve the weakest possible, we should do the opposite, and we would have this here. So this has been my presentation. I hope you have found it interesting and that you have enjoyed it. Bye.